Welcome to DAR Tutors. Today, we'll be exploring a fundamental concept in bivariate statistics, the least squares regression line. This topic is a key component of the IB mathematics analysis and approaches higher-level curriculum. By the end of this video, you will be able to, first, understand the principle of least squares regression. Second, use technology to find the equation of a regression line. And third, interpret and apply this line to make predictions and analyze data. Let's begin. When we have a set of bivariate data, we often want to see if there's a linear relationship between the two variables. We can visualize this with a scatter diagram. However, drawing a line of best fit by eye is subjective. Different people will draw different lines, leading to inconsistent results. To address this, we use a rigorous mathematical method called linear regression. The most common approach is the method of least squares. The goal of least squares regression is to find the unique straight line that best fits the data. But what does best fit mean mathematically? It means minimizing the sum of the squared vertical distances from each data point to the line. Let's visualize this. Here is our regression line, represented by the equation y equals ax plus b. We have several data points scattered around it. For each point, we can measure the vertical distance to the line. This distance is called a residual, and we'll denote it as d sub I. The least squares principle states that the best line is the one that makes the sum of the squares of these residuals as small as possible. We want to minimize the sum of d sub I squared for all n data points. We square the distances to ensure that positive and negative residuals don't cancel each other out, and to penalize larger errors more heavily. The equation of this line is typically written as y hat equals ax plus b, where y hat denotes the predicted value of y for a given x. The coefficients a and b are calculated using these formulas. A is the gradient, and b is the y-intercept. The terms x bar and y bar represent the means of the x and y variables, respectively. In the IBAAHL course, you are not required to calculate these coefficients by hand. Instead, you will use a graphics calculator or a statistics package. This allows you to focus on interpreting the results rather than on the tedious calculations. Let's see how this works with an example. Let's work through an example. We have data on the annual income and average weekly grocery bill for a selection of families. Income is our independent variable, x, and grocery bill is our dependent variable, y. The income is in thousands of pounds. First, let's construct a scatter diagram to visualize the data. We plot each point, x, y, on a graph. The x-axis represents income, and the y-axis represents grocery bill. Looking at the diagram, we can see a general upward trend, suggesting a positive linear relationship. Next, we'll use our calculator to find the equation of the regression line. The process is similar for most models. You'll typically go to the statistics menu, enter your x values into list 1, and your y values into list 2. Then you'll select the linear regression function, which is often labeled linreg ax plus b or linreg mx plus b. The calculator will output several values. The most important for us are a and b. Here a is approximately 4.1 t and b is approximately 56.7. So the equation of our regression line is y hat equals 4.18x minus 56.7. This line represents the best linear fit for our data. Now let's interpret the gradient, a. The gradient is 4.1. This means that for every 1 unit increase in x, the predicted value of y increases by 4.18 units. In context, for every additional 1,000 pounds of income, a family's weekly grocery bill is predicted to increase by an average of 4,018. The y-intercept, b, is 56.7. This would represent the predicted grocery bill for a family with 0 income. In this context, a negative grocery bill is not physically possible, which tells us that the model is not valid for incomes close to 0. This is a common issue with regression models. Now that we have our regression line, we can use it to make predictions. Let's look at two types of predictions: interpolation and extrapolation. Interpolation is making a prediction within the range of our original data. Extrapolation is making a prediction outside that range. First, let's estimate the weekly grocery bill for a family with an annual income of £95,000. Our income variable x is in thousands of pounds, so we use x equals 95. We substitute this into our regression equation. Calculating this gives us approximately 397.1 minus 56.7, which simplifies to about 340.4. So we predict a weekly grocery bill of £340. This is an extrapolation because our original data only went up to $64,000. Next, let's estimate the annual income of a family whose weekly grocery bill is £100. Here, we are given y hat equals 100. We substitute this into the equation and solve for x. Adding 56.7 to both sides gives 156.7 equals 4.18. Dividing by 4.18, we find x is approximately 37.5. This means we predict an income of $37,500. This is an interpolation, as £100 falls within our observed grocery bill range. Now let's comment on the reliability of these estimates. The estimate for £95,000 was an extrapolation. Extrapolation is generally unreliable because we are assuming the linear trend continues beyond the data we have. There's no guarantee that the relationship between income and grocery bill remains linear at much higher incomes. The estimate for a £100 grocery bill was an interpolation. This is generally more reliable, especially if there is a strong linear correlation in the data. Our calculator output would show a correlation coefficient, R, which measures the strength and direction of this linear relationship. Let's consider another example. Steve wants to see if there's a relationship between the morning temperature and his commute time. He collected data over 14 days. Temperature is our x variable and time is our y variable. First, let's calculate the Pearson's product moment correlation coefficient, R. This value, R, tells us the strength and direction of the linear relationship. It ranges from 1 to 1. A value close to 1 indicates a strong positive linear correlation, a value close to 1 indicates a strong negative linear correlation, and a value close to 0 indicates a weak or no linear correlation. Using a calculator, we find that R is approximately 0.551. This is a negative value, which means as temperature increases, commute time tends to decrease. The value of 0.51 suggests a moderate negative linear correlation. Now let's find the equation of the regression line. Again, using the calculator, we find the coefficients A and B. A is approximately 0.65, and B is approximately 57.5. So the regression line is y hat equals 0.65x plus 57.5. The negative gradient confirms our earlier observation of a negative correlation. The question asks if it's reasonable to fit a linear model to this data. To answer this, we should look at the scatter diagram. Plotting the data, we can see that while there is a general downward trend, the points are quite scattered. The correlation coefficient of 0.51 is not particularly strong. This suggests that temperature is not the only factor affecting commute time, and a linear model might not be the best fit. It's reasonable to fit a linear model, but we should be cautious about the strength of the relationship. Let's delve deeper into the importance of visualizing data. We'll look at a famous example called Anscombe's quartet. This quartet consists of 4 different bivariate datasets. Let's calculate the key statistics for each one. For all 4 datasets, the mean of x is 9, the mean of y is 7.5, the variance of x is 11, the variance of y is 4.125, the correlation coefficient R is approximately 0.8166, and the regression line is y hat equals 0.5x plus 3. Numerically, these 4 datasets are identical. If we only looked at the statistics, we would conclude they are all the same and a linear model is appropriate for each. However, let's look at their scatter diagrams. Dataset A shows a clear linear relationship. The regression line fits the data well. Dataset B shows a curvilinear relationship. A parabola would be a much better fit than a straight line. Dataset C has a strong linear relationship, but one outlier point significantly influences the regression line. Dataset D has a constant x value for all but one point, making a linear model completely inappropriate. This quartet powerfully demonstrates why it is crucial to always visualize your data with a scatter diagram before performing any regression analysis. Descriptive statistics alone can be misleading. A scatter diagram reveals the true nature of the relationship between variables. helping you determine if a linear model is appropriate or if another type of model is needed. Another powerful tool for assessing the appropriateness of a linear model is a residual plot. A residual plot is a scatter diagram where the x-axis represents the independent variable, and the y-axis represents the residuals, which are the vertical distances from each point to the regression line. A key assumption of linear regression is that the residuals are randomly scattered around zero. If this assumption holds, the residual plot will show no discernible pattern. This is what we want to see. A random scatter of points around the horizontal line at y equals 0 indicates that a linear model is a good fit for the data. However, if the residual plot shows a pattern, it suggests that a linear model is not appropriate. For example, a curved pattern, like a parabola, indicates that the relationship between the variables is nonlinear. A fan-shaped pattern, where the spread of residuals increases or decreases with x, indicates that the variance of the residuals is not constant, which violates another assumption of linear regression. Let's revisit Anscombe's quartet and look at their residual plots. For dataset A, the residual plot shows a random scatter, confirming that a linear model is appropriate. For dataset B, the residual plot shows a clear parabolic pattern, indicating a non-linear relationship. For dataset C, the residual plot shows a random scatter, but one point is a clear outlier. For dataset D, the residual plot shows a vertical line of points, which is not a random scatter. Residual plots provide a powerful visual check that complements the scatter diagram and correlation coefficient, giving us a more complete picture of the data. Let's consider a final, more complex example involving an outlier. We have data on the yield of pumpkins based on the quantity of fertilizer used. Fertilizer is our x variable, and yield is our y variable. First, let's draw a scatter diagram and identify any outliers. Looking at the plot, we can see that the point, FD 4.4, appears to be an outlier. It doesn't follow the general upward trend of the other points. Now, let's investigate the effect of this outlier on our analysis. We'll calculate the correlation coefficient and the regression line both with and without the outlier. With the outlier included, the correlation coefficient R is approximately 0.65. The regression line is y hat equals 0.04x plus 2.7. Now, let's remove the outlier and recalculate. The correlation coefficient jumps to approximately 0.99, indicating a very strong positive linear relationship. The new regression line is y hat equals 0.11x plus 1.4. The effect is dramatic. The outlier significantly weakened the perceived correlation and changed the gradient of the regression line. The line without the outlier is much steeper. The question is, which regression line should we use to estimate the yield when 15 grams per square meter of fertilizer is used? We should use the regression line calculated without the outlier. The outlier is likely due to an error in measurement or an unusual circumstance, and it distorts the true relationship between fertilizer and yield. The line without the outlier provides a much more accurate model for the data. This example highlights the importance of identifying and carefully considering outliers. They can have a disproportionate impact on your statistical analysis. Let's conclude with a brief discussion on the theory of knowledge, a core component of the IB diploma program. We've seen how to use linear regression to model data and make predictions. But how reliable are these predictions, especially when we extrapolate far into the future? Consider the example of female life expectancy. A linear regression line might show a steady increase over time. If we extrapolate this line, we might predict that life expectancy will continue to rise indefinitely. However, many scientists have proposed ceilings on human life expectancy, suggesting that the linear trend cannot continue forever. This raises a fundamental question. Is mathematical extrapolation valid evidence for dictating policy or making long-term predictions? While mathematics provides powerful tools for modeling, it's essential to remember that models are simplifications of reality. Extrapolation assumes that the underlying conditions and relationships will remain constant, which is often not the case. For example, predicting future climate change based on past trends requires careful consideration of the complex systems involved. A simple linear model might not capture the nuances of the climate. Therefore, when using regression and extrapolation, we must always combine our mathematical analysis with knowledge from other disciplines, such as biology, economics, or environmental science, to make informed and responsible conclusions. Let's recap what we've learned today. We started by understanding the principle of least squares regression, which finds the line that minimizes the sum of squared residuals. We then learned how to use technology to find the equation of this line and how to interpret its gradient. We also explored the difference between interpolation and extrapolation and their respective reliabilities. Finally, we saw the critical importance of visualizing data with scatter diagrams and residual plots to ensure that a linear model is appropriate. And we discussed the limitations of extrapolation from a theory of knowledge perspective. You are now equipped to tackle IB-style problems on least squares regression. To solidify your understanding, let's work through some practice questions. Here's your first practice question. Take a moment to read it and try to solve it on your own. The table shows the number of hours a student spent studying for a test and their score. Part A asks you to find the equation of the regression line. Part B asks you to interpret the gradient. Part C asks you to predict the score for a student who studies for 10 hours. And Part D asks you to comment on the reliability of that prediction. Pause the video here and work through the problem. When you're ready, continue for the solution. Let's go through the solution for question 1. First, we enter the data into our calculator. The x values are 2, 4, 5, 7, 8, and the y values are 60, C5, CE, 90, 95. Using the linear regression function on our calculator, we find that C is approximately 5.88 and B is approximately 48.24. Therefore, the equation of the regression line is y hat equals 5.8x plus 48.24. For part B, the gradient A is 5.88. This means that for every additional hour a student studies, their predicted test score increases by an average of 5.88 points. For part C, we need to predict the score for a student who studies for 10 hours. We substitute x equals 10 into our equation. This gives us a predicted score of approximately 107.04. For part D, we comment on the reliability. The prediction for 10 hours is an extrapolation, as our data only goes up to 8 hours. Therefore, the prediction is likely unreliable. It's also unrealistic, as a test score cannot exceed 100. Here is your second practice question. The table shows the number of ice creams sold and the temperature on 8 different days. Part A asks you to calculate the correlation coefficient R. Part B asks you to describe the relationship between the variables. Part C asks you to find the equation of the regression line. And Part D asks you to predict the temperature if 150 ice creams are sold. Pause the video and work through the problem. Continue when you're ready for the solution. Let's go through the solution for question 2. First, we enter the data into our calculator. The x values are the number of ice creams, and the y values are the temperatures. Using the linear regression function, we find that the correlation coefficient R is exactly 1. This is a perfect positive linear correlation. For part B, since R equals 1, we can describe the relationship as a perfect positive linear correlation. This means that as the number of ice creams sold increases, the temperature increases in a perfectly linear fashion. For part C, the calculator gives A equals 0.1 and B equals 8. Therefore, the equation of the regression line is y hat equals 0.1x plus 8. For part D, we need to predict the temperature if 150 ice creams are sold. We substitute x equals 150 into our equation. This gives us a predicted temperature of 23 degrees Celsius. Here is your third practice question. The table shows the number of hours a student spent on social media and their test score. Part A asks you to find the equation of the regression line. Part B asks you to interpret the gradient. Part C asks you to predict the test score for a student who spends 3 hours on social media. And Part D asks you to predict the number of hours spent on social media for a student who scores 70. Pause the video and work through the problem. Continue when you're ready for the solution. Let's go through the solution for question 3. First, we enter the data into our calculator. The X values are the hours on social media, and the Y values are the test scores. Using the linear regression function, we find that A is 7.5 and B is 102.5. So the equation of the regression line is y hat equals 7.5x plus 102.5. For part B, the gradient A is 7.5. This means that for every additional hour a student spends on social media, their predicted test score decreases by an average of 7.5 points. For part C, we predict the score for a student who spends 3 hours on social media. We substitute x equals 3 into our equation. This gives a predicted score of 80. For part D, we predict the hours spent on social media for a student who scores 70. We substitute y hat equals 70 and solve for x. This gives a predicted time of approximately 4.33 hours. Here is your fourth practice question. Pause the video and work through the problem. Continue when you're ready for the solution. Let's go through the solution for question 4. First, we enter the data into our calculator. The X values are the age of the car, and the Y values are the selling price in thousands of pounds. Using the linear regression function, we find that A is 2.2 and B is 17.8. So the equation of the regression line is y hat equals 2.2x plus 17.8. For part B, the gradient A is 2.2. This means that for every additional year of age, the predicted selling price of the car decreases by an average of $2,200. For part C, we predict the selling price of a 6-year-old car. We substitute x equals 6 into our equation. This gives a predicted price of $4,600. For part D, we comment on the reliability. The prediction for a 6-year-old car is an extrapolation, as our data only goes up to 5 years. Therefore, the prediction is likely unreliable. The rate of depreciation may change as cars get older. Here is your fifth and final practice question. Pause the video and work through the problem. Continue when you're ready for the solution. Let's go through the solution for question 5. First, we enter the data into our calculator. The X values are the hours of exercise, and the Y values are the hours of television. Using the linear regression function, we find that A is approximately 2.25 and B is approximately 21.5. So the equation of the regression line is y hat equals 2.25x plus 21.5. For part B, the gradient A is 2.25. This means that for every additional hour of exercise, the predicted amount of television watched decreases by an average of 2.25 hours. The y-intercept B is 21.5. This means a child who does 0 hours of exercise is predicted to watch 21.5 hours of television per week. For part C, we predict the television time for a child who exercises for 7 hours. We substitute x equals 7 into our equation. This gives a predicted television time of 5.75 hours. For part D, we compare this prediction to the actual data. The data shows that a child who exercised for 7 hours watched 9 hours of television. Our prediction of 5.75 hours is lower than the actual value. This difference is the residual for that data point. That concludes our lesson on the least squares regression line. We've covered the theory, the practical application using technology, and the critical importance of data visualization and interpretation. Remember, the key to success in IBAHL statistics is not just performing calculations, but understanding what those calculations mean in the context of the problem. Thank you for joining us at Dart Tutors. We hope this video has been helpful for your studies.